Hello everyone. In this video I'll be talking with you about current and voltage dividers. There'll be some very basic ones, but sometimes you have a situation where you have 3 resistors instead of 2 that you want to know a voltage divider rule with those resistors. So I'll be deriving that in this slide presentation here. So for starters, we have nodes A and B, B and C, C and D. We want to be able to know the voltage between those nodes based off of what we wish to know, and we want to have a formula for that. So to start with, using Kirchoff's voltage law, it says that the voltage distributed throughout the circuit has to add up to the source voltage. And so we'll be analyzing voltage between point A and B, B and C, C and D. And we'll call these resistors R1, R2, and R3. So VDC, breaking this into components, VDC has to equal the current going through all of these resistors, which is I. I use a generic term without any subscripts in order to indicate that this is common between everything in there. And so VDC equals this expression with IR1 plus IR2 plus IR3. And then by rearranging and isolating I, then we have VDC over R1 plus R2 plus R3. Next, we use the fact that if we multiply I by R1, we should get, or we will get rather, the voltage between point A and B, or node A and B. And so by doing that, we derive a formula that tells us VDC times R1 divided by R1 plus R2 plus R3. And when we put these values in there, all of the values that we have in our circuit, all 4 of them, then we come out with 2 volts for our value between A and B. Next, voltage between B and C. It's the same formula, it only differs by R2 instead of R1, and we get 4 volts there between B and C. Next, between C and D, we will have the same formula, it only differs by R3, and then when we put in those values for all of these terms, we have 6 volts between C and D. That is our voltage divider for 3 resistors, and these are our formulas that we'll use. Next, current divider. So I have 1 amp here, 1 kilo ohm, 2 kilo ohm, 3 kilo ohm. These are all in parallel, and this is a node up here, V, which is a voltage that's common to all of these resistors because it is in parallel. So for starters, IDC, because of Kirchoff's current law, IDC has to be the summary of IR1, IR2, and IR3. So all of those are summed. And then when we use the fact that V is common to all of these branches, then we can break it into components. And we have this expression with IDC equals V over R1 plus V over R2 plus V over R3. Next, we will isolate V and have this expression where we have IDC times R1, R2, R3 divided by R1, R2 plus R1, R3 plus R2, R3. Next, we will use the fact that voltage over our resistance here, V over R1, will give us the current through that resistor. What is that current? That current, when we use this formula that we've derived by dividing out by R1, is IDC times R2 times R3 divided by R1, R2 plus R1, R3 plus R2, R3. When we put in those values, we get approximately 545 milliamps. Next, for the current going through R2, everything is the same in this formula except instead of having R1, instead of having R2 rather, we have R1 here. And when we put in all of those values, then we have approximately 273 milliamps going through our 2 kilo ohm resistor here, which is R2. Next, for the current through R3, everything is the same except for these two terms here. Instead of having R1, R3, we have R1, R2. And when we put in our values, then we'll have an approximation of 182 milliamps. So next, what I'm going to do is run a FreeMat, which is like MATLAB script, and show these values due to calculations. Okay, so here is our FreeMat script that I have here. And so I just cleared the screen first. Then I define my functions using FreeMat syntax. Next, I have evaluated those functions, and those functions are for IR1, IR2, IR3, and then VAB, VBC, and VCD. So I'll run the script, and the values that I get are for 546 milliamps for IR1, 273 milliamps approximately for IR2, 182 milliamps approximately for IR3. Then for our voltages, we have 2, 4, and 6 respectively for VAB, VBC, and VCD. Next, what I'll do is take a look at a simulation. Okay, so for our simulation, all of the values and the circuit topologies and the way the networks are built are all the same. And so I'm going to simulate now. These are where the values are going to come up. And for the voltages here, the values will come up on these meters. So we can see we have 1 amp going in to our entire network here. And down this branch, we have 545 milliamps through R1, 273 milliamps through R2, 182 milliamps through R3. Over here for our voltages, we have 2, 4, and 6 volts for VAB, VBC, and VCD respectively. So all of that checks out very well, and that is it for what we need to verify in this particular video. So thank you for watching this video. Hopefully it was helpful for you. Have a nice day.